at would be the single replacement reaction. And it's really going to be kind of our big last one. What this is going to reference is exchanging typically a metal, a solid metal, into an ionic compound. And so what we're looking at is kind of a difference in activity. We've got a bunch of examples shown below that released or revealed a little bit faster than I wanted, but we'll go ahead and take a look at the first one, and then we'll kind of give you some time to practice the others. So if we go through and kind of align this, we're looking at our metal with, oh, come on. Of course, my technology decides to not connect, but we're looking at that metal reacting with an ionic compound, and in the process of that, doing an exchange. So what we needed to go through and do is identify those kind of common things. Note zinc and lead are both metals, and it is those metals that help to differentiate them from the non-metals of our lead sulfate. So being able to identify our metals and non-metals becomes a critical step here. This is why we came up with that differentiation earlier in the semester. Now when we go through to do the single replacement, those metals are ultimately going to exchange locations. So I'm going to pull the lead out to be by itself, and then I'll end up placing the zinc into that compound to be with our sulfate. Okay? And we've effectively done our single replacement reaction. That's roughly it. There are some kind of added complexities to this because we do need to specify phase. Okay? So the one by itself will become a solid, and the one in a compound will be aqueous. Okay? So we've got those phases in it. The last thing that gets layered in with our single replacement reactions is that we also have to be able to interpret something known as the activity series. And so what the activity series is looking at the ability for each of these metals to do the chemistry, in kind of quotes, that's happening here. And that chemistry is something that is very hidden from us. Okay? And that's why you watched that play pause it video earlier looking at oxidation states. So with a little bit of practice, hopefully what you'll be able to see is that if we look at the zinc, it starts with a zero oxidation state. Okay? And we know it's a zero oxidation state because there's no charge written there. And since it's the only element there, the charge is the same as the oxidation state. And it ends as a +2. Okay? That again becomes tricky, except that this is an ionic compound, and ionic compounds we could write out as the individual ions that made them up. How do we know it's an ionic compound? It's a combination of a metal and a nonmetal. So when we look at that, the zinc and charge and the oxidation state end up being the same thing. So 0 to +2 becomes the transition. So for zinc to go from a 0 equal balance of protons and electrons to now being positive, some electrons had to be exchanged. And in this particular case, it had to lose electrons. Okay, so that loss of electrons is something that's happening on the back end of this. Okay, at the same time, if we went through and looked at the lead, what we would notice is that it would gain electrons. Its oxidation state started at a +2 and it ends at a 0. So by gaining electrons, it becomes more negative, +2 to 0. Okay, so when we're thinking of activity, that activity is directly referencing this ability to really gain or lose electrons. The more active the metal, the more likely it gets rid of its electrons. So lithium being at the top is very, very, very active. Okay? By being more active, it wants to lose, we just color how we've been looking at this, it wants to lose electrons and thereby become a compound, okay, or go into an ionic compound. If we look at something lower in activity, it wants to lose electrons less. In all cases, it's still ranking the loss of electrons when we're looking at our activity series. So if we move to gold, we're still talking about it losing electrons. It just really doesn't want to lose electrons. The way we would use this activity series is to compare the two metals that we're evaluating. So in the case of this particular reaction, we're comparing zinc's ability to lose electrons versus lead's ability to lose electrons. Okay? So if we're now looking at it in this lose sense, which one would rather lose electrons, zinc or lead? Well, zinc being higher wants to lose electrons, which means this reaction of zinc going towards the products is very, very, very favored. Okay, it wants to do that. Okay, and when put in this situation, it will give up those electrons to lead. Let's look at the lead though, because the lead's a little confusing because we're still looking at it according to activity, which means we need to be looking at the metal. And if we look at where we're starting, we're not starting with the metal, we're starting with the ionic compound. When we're talking about these predictions, really what we're referencing is the metals and their desire to go different directions in the reaction. So if we're comparing this, these are effectively goats butting heads at each other, okay, slamming up against each other, and we're seeing who wins. Which one wants to get rid of those electrons? Because if we look, lead to go from the right-hand side to the left-hand side has to still lose electrons also. So if these goats slam at each other, zinc wants to lose electrons more than the lead, which means if we're looking at how these arrows drive into each other, the overall result is that we move towards products. What does that mean? That means that if I mix zinc solid and lead ion together on a reactant side, the end result is that the zinc will exchange with the lead to form the products shown in this chemical equation. Okay? And it's looking at their respective activities, okay, or their ability to allow that transfer of electrons. For those of you going, holy crap, this transfer of electrons is challenging, we can take a step back and we can back kind of away from all of that, and we can try and pitch it in a slightly different fashion that will work for Chem 130, but then will fall apart in later chemistry classes. Okay, so what do I mean by that? Well, let's take a look. We're again going to compare zinc, which I had in blue, and our lead in red. And instead of referencing this as activity, we're going to reference it as the companionship index, if you will, I guess. Okay, so instead of it being, say, an activity, we're looking at introvert or extrovert. That's a better way of looking at it. The higher on that list, the more extroverted the person. The lower on the list, the more introverted. So if you are higher on that list, you want to be found with other things. Okay? Lower on that list, you want to be found by yourself. So now what we can go through and do is compare our zinc and lead again. Zinc is much more extroverted. It wants to be with compounds. So what I'm going to do is look at my reaction equation and say, where do I see zinc with other things? Right there on the product side. Okay, so just looking at zinc, I would think that this reaction should occur. I should produce products because zinc wants to be with things. But lead may get in the way. Lead being lower on the list is more introverted. Because it is introverted, it wants to be by itself. Where in this big long line of an equation is lead by itself? Well, there it is. Again, by itself. And again, note on the right-hand side of our reaction, on the product side. Either way we look at it, being extroverted or introverted, our reaction produces products. We favor those products. Okay? Well, what if we favored the reactants? Well, if we favored the reactants when we mix them, what happens? Nothing. The species that wants to be with something is already with something, and the species that didn't want to be with anything isn't with anything, so no reaction occurs. So by trying to kind of identify our extroverts and introverts and where they are, be they on the reactant side or the product side, allows us to predict if that reaction actually happened. So we're really getting kind of two predictions out of this. One, what would the products be? And two, did products actually form? Okay? And that can be confusing, but the analogy I would like to use is, say, lottery. Okay? Does anybody know what they would do if they woke up tomorrow and had $1 million? Okay? You've got some plans, right? Does that mean you're going to wake up tomorrow and do those plans? Well, it's conditional on, did you get that $1 million? The same thing happens here. Our reaction when we go through to balance it out is the plan. Whether that plan actually happens is dictated by the chemistry, and that's our activity. Okay? So we have two layers of kind of interpretation that we have to move through when looking at our single replacement reactions. And yeah, because we aren't doing a different lab, we can just use that because that works out to explain nicely what's going on. Which then sets us up with practice. Okay, so we've got 3 more equations shown below. I would like you to take a second to pause and work through those. Before you freak out too much that, oh my God, you've got to memorize the activity series, you don't. Okay, remember, open notes, you can keep that activity series next to you. If in future courses you're getting class from me in person, it won't be open note, but I'll give you an activity series. Okay, and if you look at exam 1, you had an activity series in it. All of that information is going to move with every single exam so that you know it's there. Okay, so with that, please take a second, pause, click, escape, stop me talking so you can practice these next 3. You didn't actually hit pause. That's why I'm still talking. Much better. Thank you. So let's go ahead and take a look at this. Okay, so if we run the next one, our magnesium needs to go with the nitrate. And our nickel needs to be by itself. Okay. Interesting question. Actually, we won't address that yet. If we go through and deal with phases, which I started to do, but then didn't for this one. If it's in a compound, we'll call it aqueous. If it's by itself, we'll call it a solid. Deciding, did this reaction, or is this balanced? Well, no, because the nitrate, we need 2 nitrates to balance, and that's allowed because +2 - 1. Okay, so we need 2 nitrates to balance that magnesium. And we'll look at an example of that being problematic in a second. Okay, so now, did this reaction happen? Well, we would identify magnesium, and we would identify nickel. Nickel is on the introvert, magnesium is on the extrovert. Magnesium being extroverted, there we go. Nickel being introverted, there we go. Product reaction, yes, a reaction occurs. Okay. Next one. We'll exchange these silver with the chloride. Okay, again, we could go through and throw in aqueous, and I'll throw in a nice little question on that one in a second. And then we could throw in our aluminum here, and we could throw it in as a solid. We could be asked to predict and then balance and then the sum of the coefficients. And for those eagle-eyed students, you might notice that we have 3 chlorides versus only 1 chloride. An instant reflex to fix this would be to put a 3 here. And that is horribly wrong. Okay? And that is a tricky concept to deal with. If we look back at the previous one, isn't that what we did here? No. Okay, remember, for that one, I had the charges written out, right? The 2 next to nitrate in our product is different than the 2 next to nitrate in our reactant. Why? Well, the nitrate's with a different compound or with a different metal. Because it's a different metal, I need different amounts of nitrate. In this case, it just so happens that each of those metals has the same oxidation state or same charge, and that's why I need the same amount of nitrates. When we move down to the next question with our silver and our aluminum chloride, now we introduce that next issue. Silver has a +1 charge. Chloride has a -1. The formula for silver chloride is AgCl. But then chlorine doesn't balance. You're right. How do I balance the chlorine? That's balancing the equation, and I would need to change the coefficient. Okay. Why did that 3 not get to come over? Well, if we look at the 3 on our reactant side, why is there a 3 there? There's a 3 because I need 3 chlorides to balance the aluminum's charge. Why can I not put a 3 next to the chloride in the product? Well, is the chloride with aluminum anymore? No. So the whole reasoning behind why it would move or not move has changed, and that's what you have to be careful of. We're placing a number in the same location. It appears to have the same meaning, but the meaning changes. Okay? And that is a bit nasty, but you do have to watch out for that. Okay? So make sure you know why you're placing a number where you're placing it. Okay? The next question that usually comes out of that is, what about this 3 in there? That one moved across. Well, why did that one move across? What was that 3 a part of? That 3 was not to say I needed 3 oxygens to balance the nitrogen. Because if you know anything about your charges that you were told to memorize, that makes no sense. That 3 is because I need 3 oxygens and 1 nitrogen to make nitrate. That 3, placed as a subscript, same location as all of our 2s, it has meaning with the name, the identity of the compound, not the amount of the compound. And for those of you going, what? Yeah, it's crazy. We're putting numbers as a subscript and the meaning changes. Same location. We could even have identical numbers. The number as a subscript could mean the identity of the molecule or the complex ion. It could also mean the number of whatever species is there. Okay, and for those people being like, that is complete and utter nonsense, what compound or what atoms are in that circle down there? For those of you saying nickel, no, it's nitrogen and iodide. Now it's nickel. A subtle change in the letters makes a really big difference in the meaning. So we have to be very careful to know why we are writing things, and we aren't just spitting numbers and letters onto a page. Okay? That why drives your understanding of the reactions. Otherwise, all you're doing is hoping for memorization, and sometimes that works, sometimes it doesn't. Okay? So again, understand the meaning behind your actions. Clean all those arrows out of it, because we got the next part of our question. Because we now have a balanced equation, so we could look at that last one, or that silver and aluminum one. If we pull out the silver and the aluminum, there's silver, and there's aluminum. Aluminum is higher on the list, so it is more of an extrovert. Where's aluminum with something? Right here in the reactants. Silver is lower on the list, so it's an introvert, so it wants to be by itself. Here it is as a reactant, which means if I mix silver with aluminum chloride, this doesn't occur. This is a no reaction. There's no reason for this reaction to occur because silver wants to stay by itself. It's already there. Okay, so that would be a no reaction. If we go through and do the last one, it addresses the last major issue I have with single replacements, and as you move through practice with these things, you'll encounter issues like this. I need to clear all that. if we run gold with our sulfate plus copper by itself, solid, aqueous, we need to ensure that our copper sulfate was correct, or sorry, our Au gold was properly balanced. The charge on sulfate is a -2. The charge on gold is... Was I told to memorize that one? No. Well, how do I know what the charge on gold is? Well, I could look it up, and I would find it's actually variable. There's a couple different charges associated with gold. So how do I know how many golds and how many sulfates? You're right. This becomes a really crappy question to ask, because your ability to differentiate what kind of the oxidation state for gold is disappears. So if you encounter a question like this, and this is usually a horrible thing to do, assume that it's as easy as humanly possible. So the easiest charge for that gold would be a +2, so that it counterbalances the -2 of our sulfate. Okay? Which is not the best method as far as science goes, but if that's all we got, that's all we got. Okay? Last thing I like to address, just because I think it's kind of cool to talk about it, is that this activity series explains currency. Okay? So our everyday monetary financial system has been based kind of historically off of gold. And this is why we have Fort Knox with all of that gold in it. And theoretically, sort of, kind of, we're only allowed to print as much money as we have gold to support it. If we don't have the gold, then we shouldn't be printing money. We print money like mad dogs, and we definitely don't have the gold to support it. But different class. Meanwhile, why was gold selected as the material to base our currency off of? Because it wasn't just now. Gold has been our currency for ages. Doubloons, gold, okay? Silver. These were things that we used as our currency. Why did we pick those and not, say, aluminum or copper? Okay? The reason has to do with its activity. Okay? For a currency, if I'm going to measure out gold and say, here's a gold piece, it's the mass of the gold that gives the value. So I give you a bigger piece of gold, you're happier, you have more money. Okay, so it's a mass. If we use something like aluminum or copper, those materials react with oxygen in the air and other metals and turn into ions. And when they turn into ions, they turn into solution, and they dissolve into the world around us. So we would lose our currency very, very quickly. Okay? The big example I'd like to really push on this is just throw it to the extreme. Instead of gold, we did lithium. Lithium is so reactive that when you put water on it, it dissolves. That's pretty reactive. So if our entire currency was based off of lithium, we would just have to attack Fort Knox with maybe a fire, set something on fire and let the sprinklers dissolve it all away. Or just go in with water guns and just spray water all over the substances. Okay? So activity plays a role in our currency. Right? It also plays a role in our jewelry. If you think of our jewelry, we have gold, platinum, and silver as our primary forms of jewelry. Why? Anybody ever had like a nickel ring or a nickel earring that they thought was silver? Okay? Those people that have had that experience know what it does. It stains your hand. Okay? Or it stains your ears. Okay? That material reacts with the water and materials in your skin and dissolves the metal into your skin, and it discolors it. Okay, so again, what do we want for jewelry? We want the things that don't react. Silver, platinum, and gold are right at that leave me alone reaction, which means we can turn them into jewelry, we can wear them, and we don't have to worry about our face melting off. Cool. Lithium, we would have to worry about that. Okay. Regardless, where this really pushed or started was looking at our electrons, or the transfer of electrons. And that last thing I just want to address, some metals are super reactive. They react with water. We talked about that with lithium. You don't need to know which ones. I just want you to be aware that they are that active. They're cool. You can look them up online. People throwing bricks of lithium or sodium into a lake. Highly dangerous and highly bad for the lake. But regardless, transfer of electrons, what we're looking at is oxidation and reduction. And this was that play pause it video you watched. What that was looking at is oxidation state and comparing it to charge. And they are very similar concepts, but have vastly different kind of applications. Oxidation state only applies to an atom. Okay, that's it. Charge applies to anything. Well, why would that matter? Well, really, in both cases, it's the balance of protons and electrons in whatever thing you're evaluating. If it's an atom, it's the balance of protons and electrons on that atom. That makes sense to call it oxidation state. So I'm differentiating that from, say, a molecule that has a whole bunch of different atoms, and they all have different balances of protons and electrons. And when I combine them all together, I get a new balance. Okay? That's our differentiation between these. So really, they are kind of the same thing, protons and electrons. It's just to what you're referencing. Okay? The next part that kind of gets layered into this is the oxidation state is never explicitly stated. The charge, however, as we talked about back in Unit 1 with our atomic notation, is always specified. That charge is specified in the upper right-hand corner every time we write out a compound. And in most cases that you've been dealing with, that charge was 0, which is why we didn't have to write anything. But we can use that information based off of our formula here to determine the oxidation state for each of the atoms found within that individual compound. And that's what these rules are there for. You're just applying these rules to determine those oxidation states. Because once you have those oxidation states, you can now see that the oxidation states have changed, and we now see that there's a transfer of electrons. Well, why does that become important? Well, transfer of electrons does result in the change in phases, so it might be nice to know that. Well, why don't we just show electrons in an equation? Well, look at our equation. Where do you place the electrons? They're really everywhere. Okay? And I can't just have them fall off and exist on their own because they're incredibly unstable. Okay? Think back to our energy diagram, okay, of all of the different orbitals. Our highest energy electron was the one that wasn't associated with anything. I want it to be associated with a molecule. In fact, our electrons are so incredibly high energy that we use that to drive our society. That's why we have electrical outlets. Right? Electrons are so high in energy that I can plug in a device and the electrons are naturally going to flow like water down a mountain to cause a motion or some light to turn on. That's pretty cool. But our electrons have to be that high energy to do anything with. Okay? So what we want to do is recognize and see them or come up with ways to manipulate them. And that's ultimately our oxidation state. Okay? To do that, we really have to define oxidation and reduction, which is our loss of electrons and gain of electrons. Okay? Some people would say, well, why don't we just say loss of electrons? Well, oxidation and reduction are ancient terms. Oxidation was noticed when we took an iron boat and it started to rust. And we noted that the parts that weren't exposed to air didn't rust. That meant there was something in the air causing the rust. We called that oxidation because the thing in the air was oxygen. Okay? The reduction is kind of the opposite. If I keep oxygen out of the system, okay, remove it, I've now reduced the amount of oxygens. We're looking at reduction. Okay? So the terms kind of grew up as oxidation and reduction first. Then we get Thomson's model with electrons saying that's a loss and gain of electrons, and now we have to merge those two systems. Okay? You are responsible for associating those terms. My recommendation, as per the play pause it video, is Leo says Gur. I really think it's dumb to call it oil rig. Just my record or my 2 cents, but it really doesn't matter as long as you get it right. So if we look at the reaction shown here, we should be able to go through and determine what was oxidized, what was reduced. To do that, we have to be able to pull out what are the individual reactant atoms or elements, what were they in the reactants, what were they in the products, what were their oxidation states, to then see how they changed. Right? So one potential way to do this before we even start is be like, do I need to do this? There are some oxidation states that are obvious. Anything by itself has an oxidation state of 0, assuming nothing is specified as a charge. Okay? So if I look for that same silver over here, it's not by itself. It by definition must have changed. I don't know what it changed to necessarily yet, but I know it changed. That means I have to look at oxidation states. So if we look at silver, it started as a 0. If we look at it as the product, we would have to kind of separate that as an ionic compound into the individual ions. I know chloride is a -1, which then means silver must be a +1. I could have also memorized that silver is a +1 when it's an ion. What happened to the silver? It went from a 0 to a +1. Okay? That means it lost electrons. So I did a bad job color coding that. Okay, and that seems a little bit weird. You're like, but I gained. You're right. You did gain an oxidation state. Okay, but remember, we're talking about the gain and loss of a negative thing. That negative thing is what's going to plague all of our calculations. Okay, that's a challenge to deal with. This is why nobody likes debt, because it's negative. The loss of a negative equals a positive. Okay? If we go through and look at the next one, let's say aluminum. Again, this is an ionic compound, so we can split it into the ions. Chloride's a -1. Aluminum, I'm required to know, is a +3. If I didn't do that, is there another way I could have figured it out? Well, there's 3 chlorides. The aluminum had to balance it. Chloride's contributing -3 to the overall system, which means aluminum has to balance that as a +3. Aluminum in the product side is by itself. There's a 0. So we go from a +3 to a 0, or we reduced the number. We reduced the number because we gained electrons. That's our reduction. What happened to the chloride in the course of the reaction? Well, go through and take a look at it. Chlorine started at a -1, ended at a -1, nothing happened to it. It really wasn't involved in the chemical reaction at all. Our chemical reaction was centered on the silver and the aluminum. For those people that happen to notice that mistake, you're right, that is a mistake. Feel free to comment about that and play pause it and see if you got an idea on why that's a mistake. Okay? That mistake doesn't change any of the answers on this question or on this page, so we're really good to just go ahead and move on. Which then gets us kind of to the last big conceptual aspect behind this is agents. Okay, these agents are now referencing not an atom that was oxidized or reduced, but the thing that contained the atom that was oxidized or reduced. Okay, and really how it acted. Okay, so if I think about a Russian spy, okay, a Russian spy doesn't come into the US and act like a Russian. Because everybody goes like, dude, you're a Russian. I'm not going to show you anything sensitive. A Russian spy would come into the US and act like a American citizen, so that they could get valuable intelligence to send back to Russia. So your spy always looks like the other thing. Why is that important? We'll look at our definitions. An oxidizing agent, Russian spy, is the molecule that stole electrons from another compound. So our Russian spy stole data from the US. Okay? To do that, it had to steal those things, and thereby it was reduced. that was clearer in my head, and I apologize that the SPY analogy didn't quite work there. An oxidizing agent caused something else to be oxidized. Okay? If that thing was oxidized, if that thing lost electrons, the agent had to force that to happen. The only way that other thing could lose electrons is if something took them. Our oxidizing agent was the thing that took them. So the oxidizing agent is actually reduced. Oh, maybe. So if we look at the reducing agent then, the reducing agent causes something else to be reduced. Well, if it was reduced, that means it gained electrons. So if I was a reducing agent and caused you to gain electrons, you had to get those electrons from somewhere. Oh, you got them from me. So I lost electrons. Lost electrons, oxidation. Leo says good, right? Oxidized. The reducing agent is oxidized. The oxidizing agent is reduced. Okay? I know they sound like opposites and it's confusing, which means anytime you see the ing or agent or ant, that ant thing is floating in there too. At the end, ow, I just got electrically shocked. Okay? Those are tip-offs that you now need to be very careful with your assessment. Usually what I would do is the instant I see oxidizing agent, I would go, this was reduced. And because for me, looking at an equation and deciding it was reduced, it isn't obvious. What is obvious is that reduced is gain of electrons. The instant I see that oxidizing agent, boom, those words get put on there. Now I don't have to think about it. There's not a pause of, well, what was that process? What do I connect? It's there immediately. Reflex. The faster you can get through that reflexive, I'm dumping data that I know is true, the better off you'll be. Right? So what does that then leave us with? That leaves us with a ton of practice. Okay? So we got 3 equations here. You should be able to go through, determine the oxidation state for every single atom, both on the reactant and product side. Then be able to compare atoms across to decide was it oxidized or reduced. If it was oxidized or reduced, then also add what was the agent associated with it. That's a lot of work. Okay? So we're going to do this a couple ways. One way I'm going to say you should pause and you should just do that. We're already at 38 minutes. That's a lot of time for me to go through and just write that all out. So I'm going to say pause, do that work real quickly. Now that you're back with me, there's an answer. There's an answer. There's an answer. So real quick, the answers are there. Now you can pause and check your work. If you didn't pause, shame on you. I'm getting rid of all of those answers. I know you could rewind. That's irrelevant. Okay? Hopefully with that, you understand what's going on. You've got some practice now to manipulate this. Don't worry about balancing reactions. Just identify reduced, oxidized, oxidizing agent, reducing agent. Do that for me and you got it. Okay. Thanks for listening. Whoa, 5:19.